Welcome everybody once again. So this is our fourth class for module 3. We are studying moment distribution method. So today we are going to see the next concept in moment distribution method, that is how will you analyze a continuous beam or an indeterminate structure using moment distribution method when there are settlement of supports or sinking of supports. So today we are going to see how to analyze the indeterminate structures when some supports sinks. So sinking of supports. So the procedure is the same, and when there are sinking of supports, when the support sinks, when there is settlement of supports, the only difference is while calculating the fixed end moments. So here we have two cases. First is case 1. So case 1 is when the beam is fixed at both the ends. Okay, when the beam fixed at both the ends, okay, so when your beam is fixed at both the ends, our fixed end moment, that is, suppose if you are taking this end as A, this as B, and we have some unit load, concentrated load or UDL, then our fixed end moment MFAB becomes this fixed end moment, that is MFAB, because of this external loads. Okay, because of the external loads, that is what we have done so far. That is, when there is a UDL, when there is an UDL, your fixed end moment MFBC will be equal to your fixed end moment will be equal to plus or minus WL square by 12. If there is a concentrated load, our fixed end moment will be equal to plus or minus WAB square by L square and plus WAB square by L square. So that is the fixed end moment due to the external loads. Plus you have fixed end moment, that is MFAB, due to the sinking of supports. Okay, so this MFAB due to the sinking of supports will be equal to, now I will write, okay. So here, see, for this, due to external loads, your formula will be plus or minus WL square by 12. If it is concentrated load, you have minus WAB square by L square and plus WA square B by L square. Okay. Now, if there are sinking of supports, your fixed end moment becomes plus 6EI del by L square. And if the sinking of supports is downwards, if the net sinking is downwards, then that is negative. If the net settlement is upwards, it becomes positive. So hope you understood. So this is for the first case. Now we will move on to the second case. Case 2. Case 2 is when the beam is fixed at one end and freely supported at the other end. Fixed at one end and freely supported at other end. So you will have one end is fixed and the other end is freely supported. You may have external loadings also. So if that is the case, your MFAB will be equal to MFAB due to external loads plus your sinking of supports is equal to 3EI del by L square. And if the settlement is downwards, it is negative. If the settlement is upwards, it is positive. So these are the two things you should keep in mind. Now we will solve a problem. So our first problem is, we will move on to our first problem. So our problem is a continuous beam ABCD. So a continuous beam, we have a continuous beam A, B, C, D. Okay, continuous beam ABCD is fixed at both the ends. So A is fixed and D is also fixed. It is fixed at both the ends. Now, calculate the moment induced at the ends if support B settles by 30 mm. So at B you have a simple support and this B is settling by 30 mm. Okay, so at B you have a settlement of 30 mm. Now draw the bending moment diagram and the deflected shape of the beam. The other things given are the span length AB is 3 meter. AB is 3 meter. The span length BC is 2 meter. And the span length CD is also 2 meter. The other things what are given in the problem is the values for E and I is given. E is given as 2 into 10 raised to 5 Newton per mm square and the value of I is given as 3 into 10 raised to 6 Newton per mm raised to 4. And this I is constant everywhere it is I. Now for this problem, how will we solve this problem using moment distribution method? See, there is no external load but there is a sinking of supports. So as usual, our first step is step 1. So step 1, we will find the fixed end moments. So first for the span AB, our MF AB will be equal to, there is no external loads, so fixed end moment due to external load is 0 plus, you see for MF AB the far end is, that is intermediate support. So intermediate supports are considered as fixed support. So what we get is for fixed support, if the far end is fixed, and there is a sinking of support at B, it sinks by 30 mm. So the net sinking is, net settlement is minus 30 mm. It is settling downwards, okay? So it is minus 30. So what we get is minus 6 EI del by L square. So that is equal to minus 6 into, see the values for E and I is given in the problem. So the value for E is 2 into 10 raised to 5 into I is 3 into 10 raised to 6. Okay. Into the settlement is 30. 30 divided by, see if you put here plus, you can give here minus 30 divided by L square. Now see, this E is given in terms of Newton per mm square and I is given in terms of mm raised to 4 and delta is given in terms of mm. So everywhere the unit is Newton and mm. So we will convert this L into mm. So the span length is 3 meter. So we get 3000 square. So MFAB will be equal to minus 12 kilonewton meter. We get minus 12 into 10 raised to 6 Newton mm. So that is equal to minus 12 kilonewton meter. Now similarly, our MFBA will be equal to 0 plus, because the far end is fixed, that is intermediate supports are considered as fixed support. So 0 plus 6 EI delta by L square. So we get the same value, there is no change. Again, that is also equal to minus 12 kilonewton meter. Now we will move on for the next support, BC. So MFBC will be equal to, see, in BC we don't have any external loads, but this B sinks by 30 mm, right? B sinks by 30 mm. But you see, when you are considering from B to C, it is like this, right? Here it is B, here it is C. So from B to C, it is 30 mm. See, from B, C is 30 mm upwards. That means this should be considered as positive. From A to B, the sinking of support is like this, right? A, B. So from A, B is settling by 30 mm. So this should be considered as negative. So now MFBC will be equal to, we don't have any external loads, so it is a 0 plus, when we take BC, it is intermediate support. C is intermediate support, so that should be considered as fixed support. So 0 plus 6 EI del by L square. So 6 into E is 2 into 10 to the power of 5 into I is 3 into 10 to the power of 6 into, here delta for BC, delta is taken as positive. So it is plus 30 divided by, the span length is 2 meter. So it is, we are converting it into mm. So 2000 square. We get plus 27 into 10 to the power of 6 Newton mm. That is nothing but 27 kilonewton meter. Similarly, we will find the fixed end moment for the span CB. So MF CB is equal to, so that is also same, we don't have any external loadings, plus 6 EI delta by L square. So that is the same as 27 kilonewton meter. Now we will move on to the next span, third span, that is MFCD. So you see the span MFCD. So CD is like this, right? There is no sinking of supports in the span CD. That means your fixed end moment due to external loads is 0 and the fixed end moment due to the sinking of supports is also 0. So MFCD is 0. Similarly, our MFDC is also 0. Okay. Now you can proceed your problem as usual. So the differences, see, when there is a sinking of supports, the difference is only in the calculation of fixed end moments. Now we will move on to our distribution factor, that is our step 2. So for determining the distribution factor, we will consider the joins first. So how many joins we have? We have two joins B and C, right? B and C. Now we will take the members. At B we have the members BA and BC. At C we have the members CB and CD. Now we will find the relative stiffness. Relative stiffness small k. So when you consider BA, see everywhere here it is fixed supports, right? At A it is fixed support, B and C are intermediate supports, so we will consider it as fixed support. D is also fixed support. So BA it is fixed support, so relative stiffness is I by L. I by L. So we get I by L is 3 meter. You can convert it into mm also. Okay. But finally everywhere I gets cancelled, so that I am keeping it as I. Now for BC, it is I by L. So that is equal to I by 2. For CB, everywhere it is fixed. So I by L, I by 2. CD, D is fixed support. So I by L, I by L is 2. Now we will find the sum, that is sigma K. Sigma K. Sigma K is equal to, adding I by 3 plus I by 2, we get 5I by 6. I by 2 plus I by 2, we get it as I. Now we find the distribution factor. Distribution factor is equal to K by sigma K. So I by 3 divided by 5I by 6, we get 2 by 5, that is 0.4. Now I by 2 divided by 5I by 6, we get 3 by 5, that is 0.6. I by 2 divided by I, we get 0.5 and 0.5. See, the summation should be equal to 1. Okay, if you add these both, you should get 1. Add, you will get 1. So at a point, at a joint, your distribution factor should be equal, the summation of the distribution factor should be equal to 1. That is the meaning of that. Now we will draw our moment distribution table, right? Okay. So step 3, we will write here. Step 3 is our moment distribution table. So for the drawing the moment distribution table, we have totally from A to D, we have 4 supports, A, B, C, D. We will write the supports or the joints, okay. So our joints are A, B, C and D. So at A, see everywhere it is fixed, right? D is fixed, A is fixed, B and C are intermediate supports, and our members are AB, right? At joint A, we have AB, at joint A, we have AB, at joint B, we have the members BA and BC. At joint C, we have the members CB and CD. At joint D, we have DC. Now we will write the distribution factors. Before that, we will draw a line here. Okay. Now distribution factor is for B, for joint B, you can see for joint B the distribution factors are 0.4, 0.6. At joint C the distribution factors are 0.5 and 0.5. So here it is for BA the distribution factor is 0.4. For BC, the distribution factor is 0.6. For CB, the distribution factor is 0.5. And for CD, the distribution factor is 0.5. Okay, now we will write our fixed end moments. So what is our fixed end moments? Fixed end moments, we have calculated this in our first step. So the fixed end moments are minus 12 for AB and BA also it is minus 12. For BC 27 and for CB it is 27. So fixed end moments are minus 12, minus 12 plus 27 for BC plus 27 for CB. For CD and DC, since there is no external loads and there is no sinking of supports, so we do not have any fixed end moments here. Okay, so once we have determined the fixed end moments, now we will go for, because the extreme supports are fixed support, we have to go for balancing. Otherwise, we will go for releasing, right? If the end supports are not fixed, we will go for releasing. If the end supports are fixed, we will go for balancing. So balance it, minus 12 plus 27 multiplied by 0.4. Add minus 12 and plus 27. Multiply the value by 0.4. We get plus 6. So for balancing, we have to give it as minus 6.00. Again, add minus 12 plus 27. Multiply it by 0.6. We get the value as plus 9. So balancing, we have to give minus 9. Now, at C, it is plus 27. So plus 27 multiplied by 0.5, we get plus 13.5. So balancing, we will give minus 13.5. So here also the same value, so minus 13.5. Okay, now we will go for carryover moments. So the moments, balanced moments will be carried to the nearer supports. So the next step is carryover. Carryover, as I have told you earlier, the carryover will be, that is the sharing of moments will be between A and B for the span AB, between B and C for the span BC, between C and D for the span CD. So when we are considering the span AB, that is for AB and BA, right? These both ends, AB and BA, since A is fixed support, from A, that is fixed extreme support, there is from A, load is not transferred to B. But from B to A, half of the load is transferred. So we get here minus 3, minus 3.00. Now between B and C, in the span BC, both are intermediate supports. So there is transfer of moments between B and C. So minus 9 divided by 2, we get minus 4.5. And minus 13.5 divided by 2, we get minus 6.75. Now when we consider CD, D is fixed support. So from D is fixed extreme support. So from D there is no transfer to C. From C there is transfer, right? So minus 13.5 divided by 2. So it is minus 6.75. Now we will go for balancing. So there is no load to balance at fixed support, fixed extreme support. At B, minus 6.75 multiplied by 0.4, we get minus 2.7. So balancing it is plus 2.7. Minus 6.75 multiplied by 0.6, we get minus 4.05. Balancing it is plus 4.05. Similarly, at joint C, it is minus 4.50 multiplied by 0.5, we get minus 2.25. Balancing it is plus 2.25. Here also same value, it is plus 2.25. At fixed support, there is no balancing, right? Now we will go for carryover. So carryover moments and then balancing. So from fixed support, there is no carryover. In the span AB, only from B it is carried to A. So how much is carried is plus 2.70 divided by 2. So it is 1.35 plus 1.35. Now between the supports B and C, both are carried. So 4.05 divided by 2, we get plus 2.03. And 2.25 divided by 2, we get plus 1.13. Now, okay, from D there is no transfer of loads, transfer of moments. From C the moment is transferred. So 2.25 divided by 2, we get plus 1.13. Now we will balance. Plus 1.13 multiplied by 0.4. I will give you the values. You know how to balancing, right? So here there is no. We get minus 0.45. You balance it in the same manner. We get 0.68. We have done lot of problems. So minus 1.01, minus 1.02. Now we will go for carryover. It is minus 0.22. Here carried. So we get minus 0.5. Minus 0.34. Minus 0.51. Okay, now we will go for balancing. We get plus 0.20 plus 0.30 plus 0.17 plus 0.17 this. Now once again we will go for carryover, the next iteration, that is carryover and balance. So 0.10, 0.08 plus 0.15, 0.08. So balancing we get minus 0.03, minus 0.05, minus 0.08, minus 0.07 and this. Again last one more iterations, the carryover. So balance. Minus 0.02, minus 0.04, minus 0.03, minus 0.03. So balancing we get plus 0.02, plus 0.02, plus 0.01, plus 0.02, So that's all. And for the last step, see, when we are stopping the iteration, you have to stop with after carrying. Okay, you have to stop with carrying. So the last, for the fixed support, for the extreme fixed support, there will be carrying. So 0.02, it is 0.01, and from here 0.01. So with this we will stop. So last step is balance and carry over. Carry over to the end supports. So now you can add all the moments from the fixed end moments. That becomes your final moments, final end moments. Okay. So our final end moments are minus 12. You have to add every values. That is minus 12, minus 3 plus minus 3 plus 1.35 minus 0.22 plus 0.10 minus 0.02 plus 0.01. You get minus 13.78. Similarly, when you add everything in the for the span BA, you get minus 15.56. You get plus 15.56 plus 12.15 minus 12.15 and minus 6.07. These are your final end moments. So step 4, we will write the final end moments. Okay. Step 4, the final end moments. So your final end moments are MFAB, MFBA, MFBC, MFCB, MFCD and it is not MF. MF means it is fixed end moment, right? This is end moments. So MAB, see, I'm so sorry if I have used MFAB in the previous problems. Please remove that. That is MAB, okay? MAB, MBA, MBC, MCB, MCD and MDC. So what we get is minus 13.78 kilonewton meter, minus 15.56 kilonewton meter, plus 15.56 kilonewton meter, plus 12.15 kilonewton meter, minus 12.15 kilonewton meter and minus 6.07 kilonewton meter. See, at B the summation is equal to 0, at C the summation is equal to 0. Now we will draw the bending moment diagram. So here for drawing the bending moment diagram there is no need of finding the simple beam moments. The reason is there is no external loadings. Because there is no external loadings, there is no need of determining the simple beam moments. Okay, so how will we draw our bending moment diagram? Okay, so this is A, B, C and D. Our MAB is minus 13.78. So minus 13.7. See, when there is a sinking of supports, sometimes you may get some confusion for drawing the bending moments. Okay, so that how you can do is, at A it is minus 13.78. So if it is minus 13.78, it is anti-clockwise, right? Anti-clockwise, you can try to draw an anti-clockwise here. Okay, we will try to draw an anti-clockwise. See, that means this is pointing upwards, right? So, this minus 13.78 comes here. 13.78 kilonewton meter. Here there is no simple beam moment diagram. Okay. At B, again it is minus 15.56. See, normally we get positive, right? Now here it is minus because there is a sinking of supports. So minus, you draw anti-clockwise, pointing downwards, right? So you have to mark it downwards. 15.56 kilonewton meter. Then it is plus. At B, you draw a clockwise moment from out. So you have to take from the outside, right? It is pointing downwards. So it is 15.56. Next, at C, it is plus 12.15 clockwise, pointing upwards. So here it is 12.15 kilonewton meter. Now it is minus 12.15 anti-clockwise, pointing upwards. So minus 12.15 kilonewton meter. At D it is minus 6.07. So anti-clockwise, it is downwards. So here it is 6.07 kilonewton meter. So your bending moment diagram becomes like this. Okay. So what is the meaning of that? See, this is, here you have the negative bending moments. Here, this portion you have negative and here you have positive. See, this portion, half of the portion you have negative and half of the portion you have positive. Then up to this you have positive. Then you have negative. Then you have negative. Okay. Sorry. So your net bending moment is now we will draw our deflection diagram. So our deflection diagram becomes like this. Okay, I will explain you this. It's clockwise, anti-clockwise. Here when you are taking the section, anti-clockwise and anti-clockwise. See, that means in this portion, it is anti-clockwise, right? You have the negative bending moment. Here you have the positive. And in this portion you have positive, here you have the negative, here it is negative, and here it is positive. Okay. Now, our deflection diagram will be, see, change from plus to minus or from minus to plus. So here we have a point of contraflexion. Now at support B, it is settling down. So your support will be here. Now here there is positive to negative. There is a change. So here you have a point of contraflexion. You have the support C here. A, B, C and D. A, B, C and D. So now at this point you have a contraflexion. So our deflection diagram becomes like this. Okay, this is our deflection diagram. And this is our bending moment diagram. So that is all for today. Thank you. We will see the remaining problems in the next class.